Okay, this is chapter 8, Vectors and Parametric Equations, page 1. This is from 8.1 and 8.2, Geometric and Algebraic Vectors. A vector, and also in physics you guys would talk about vectors, is a quantity that has both magnitude and direction. And here's an example of a vector. A vector I think of as like a directed line segment. Magnitude describes the length of this vector, and the arrow describes the direction. So we could designate that as vector A, or we can call it vector PQ. And order matters. PQ meaning it starts at P and it ends at Q. And it's like a directed line segment. It doesn't go on forever. The arrow tells you where it ends. A two-dimensional vector is an ordered pair of real numbers denoted in component form as A comma B, where A and B are the components of vector V. We could also say the standard representation of components A and B is the arrow from the origin 0, 0 to A comma B. So if we want the standard representation as we see in this example here, we always start at the origin and we end at the component. The magnitude of vector V is the length of the arrow, and so the magnitude describes the length of the arrow, and then we could say the direction of vector V is the direction in which the arrow is pointing. So here we can see the arrow is pointing this way. So the magnitude is the length. The direction of the vector is the direction, like north, south, west, or east, or somewhere in between, which the arrow is pointing. Vector O is called the zero vector. And the zero vector, the components would just be 0 and 0. It's the zero vector because it has zero length and no direction. Arrows with the same length and direction are called equivalent vectors. So bottom of the page, determine the magnitude and direction angle for each vector. So the first one, 3, 2, I'm going to plot this like a normal ordered pair, 1, 2, 3, up 2. And we're always going to start at the origin, and we end at the point 3, 2, where I'm going to put an arrow. Again, it's a directed line segment. So if we want the magnitude and direction angle, I can turn this into a right triangle. And the magnitude describes the length of the vector. So if we went over 3 and up 2, it's really just Pythagorean theorem. A squared plus B squared, and then the square root. So we could say the magnitude equals square root of 13. And then for the direction angle, I can call this theta. Again, we're starting at 0, 0, ending at 3, 2. So if I want the direction angle, I could just use SOHCAHTOA. It's a right triangle. So I could say tangent of theta equals opposite over adjacent, which is 2/3. So if we want the direction angle, I'm going to just go inverse tan of 2/3, which I could just type in on the calculator. So if I go inverse tan of 2/3, and I'm in radians, so I got to change my mode to degrees. So let me go to settings, document settings. So anyways, we'll try this again. I'm going to go inverse. Let's see if that, okay. Let's try it again. Inverse tan of 2/3. 33.69. So it's about 33.7 degrees. And then last one from this page, determine the magnitude and direction angle for a vector whose components are -2, -5. I'm going to just draw another triangle. I'm going to go left 2, down 5 from the origin. Here's the vector. If I turn this into a right triangle, I'm going left 2, down 5. So for the magnitude, it's just Pythagorean theorem. A squared plus B squared equals C squared, and then take the square root. So the magnitude, I got square root of 29. Now, the direction angle, we're going to have to be careful because we're in quadrant 3. So if I go inverse tan of -5 over -2, which I can do right now, which is really 5/2, I get 68.2 about. So if I put that in for this angle, that is not the answer because you're in quadrant 3. That's the reference angle. So the distance you'd have to go around is 180 plus 68.2, which is 248.2 degrees. That would be the direction angle for B. So these are the examples from page 1 from chapter 8.